So we are back with proofs. We did proofs by deductive reasoning, and we did proof by contradiction. In general proofs by giving examples. We looked at identities. We are now looking at another method called mathematical induction. So deductive reasoning usually starts from a statement which is true and then goes on reasoning using that true statement and finding out more information. Inductive reasoning works in the other way around. It goes from specific cases and generalizes it. Let's look at two examples and see what is the procedure or the process that we follow for inductive reasoning, and which is called proof by mathematical induction. So the first question here says 5 raised to n plus 9 raised to n plus 2. Use mathematical induction to prove that this is divisible by 4 for n belonging to all positive integers. It's a good thing to recognize here that writing it in correct mathematical notations is very important. It is going to be important for your mathematical exploration as well. So communicating in the right kind of notations is important, and being able to read as well, right? So when this kind of information is given in problems, you should be able to read it clearly and understand what it is saying. So here n belonging to positive real integers means values which are whole numbers and positive numbers, so 1, 2, 3, 4 and so on. So for all positive integers this must be true. So let's try to prove this. So the statement is 5 raised to n plus 9 raised to n plus 2 is divisible by 4, correct? Now let us start, and inductive reasoning, like I said, starts with specific cases and goes to a generalized case. So the first situation we will look at is, let n be 1 and let us see what happens to this statement. So 5 raised to 1 plus 9 raised to 1 plus 2 is equal to 5 plus 9 is 14 plus 2 is 16, and 16 is divisible by 4. So the statement is true for n equal to 1. So one specific case. Now the next step is to assume that it is true for some n equal to k. I don't know which value of k is, but k is a positive integer like the condition in the problem, and it is true. If it is true, then 5 raised to k plus 9 raised to k plus 2 must be some integer multiple of 4, because it is divisible by 4, and therefore that's the whole idea of divisibility, correct? And now and this is assuming n equal to k is true. The statement is true for n equal to k. Now using this assumption and the fact that it is true for n equal to 1, let's find out what happens for n equal to k plus 1. So the expression would now become 5 raised to k plus 1 plus 9 raised to k plus 1 plus 2. And we are going to use our laws of indices here. 9 times 9 raised to k plus 2, and well, 5, 9 are not really multiples of 4, right? So let me divide this 5 into a multiple of 4 and the other number. Same thing, this 9 also is a multiple of 4 and the other number, and plus this 2 as it is. And then I have 4 times 5 raised to k plus 8 times 9 raised to k plus what is left is 5 raised to k plus 9 raised to k plus 2. Now this, if you recognize from our previous assumption, 5 raised to k plus 9 raised to k plus 2, we assume that is divisible by 4 and therefore is an integer multiple of 4. And if you look at this expression, this is definitely divisible by 4 because I am able to take 4 common. So together this entire thing is divisible by 4. So essentially what we established is n equal to k is true has led to the fact that n equal to k plus 1 is true with respect to, of course, the statement. Therefore n equal to 1 is true will lead to what? Will lead to n equal to 2 is true, n equal to 3 is true, and so on. So for all positive integers, the statement that 5 raised to n plus 9 raised to n plus 2 is true. Again, let's go back and look at the steps. Inductive reasoning starts with a specific case like n equal to 1. It assumes that the statement is true for some n equal to k, and then using that assumption, it shows what happens for n equal to k plus 1. If n equal to k is true is leading to n equal to k plus 1 also becoming true, then the n equal to 1 is true will lead to n equal to 2, 3 and everything true. Here what is important is a little bit of knowledge of arithmetic or algebraic manipulation, that how do I group terms, recognizing what I have for n equal to k is true, what is it giving me, and being able to do those kind of changes is what is the most essential skill in mathematical induction. Let's look at a second example, and the example says prove that the summation of 1 upon 2r minus 1 and 2r plus 1. What is this 2r minus 1 and 2r plus 1? If you see, they seem like two consecutive odd numbers, correct? So the product of two consecutive odd numbers, the reciprocal, is equal to n upon 2n plus 1. And again, this is true for n belonging to positive integers only. So let's write down that statement. Summation for r equal to 1 till n, 1 upon 2r minus 1 into 2r plus 1. Let's write down how does this look like. So for example, when r is 1, so this will be 2 minus 1 is 1 and 2 plus 1 is 3 plus 1 upon. When r is 2, this will be 3 times 5 plus 1 upon 5 times 7 and so on. And what is the right side of statement? If you look at what is it true equal to, they're asking you to prove that it is equal to n upon 2n plus 1. N upon 2n plus 1. So in this case, if I do this kind of summation till r is some 7, for example, then this should lead to 2 times 7 minus 1 is 13 times 15, and this should equal to 7 upon 50. Okay, if I am going till 7. So this is something that the proof is expecting us to do, and we are using mathematical induction again. So we start with n equal to 1. Okay. So for n equal to 1, what happens? There is only one term. So the expression LHS will be 1 upon 1 times 3, so which is 1/3. And RHS will be n is 1, so 1 upon 3. So LHS is equal to RHS, therefore true for n equal to 1. Okay. For n equal to k, assume true. So this is the general procedure for mathematical induction. So what am I assuming? I am assuming that summation of r equal to 1 to k of 1 upon 2r minus 1 into 2r plus 1 is equal to k upon 2k plus 1. I am assuming this is true. And now with this assumption being true, I want to find out what happens when n is equal to k plus 1. So I am doing a summation of r equal to 1 to k plus 1 now. But instead of writing directly k plus 1, what I want to do is, I want to split this summation till k plus 1 terms to summation till the kth term. Why am I doing that? Because I have a result from the assumption before. Plus, what should be the k plus 1th term? If you substitute the k plus 1 in place of r, you will get 2k plus 2 minus 1. So 2k plus 1 times 2k plus 3. So this is what I am getting by writing the statement, right? And my assumption is that this is true for till the first k term, so I'm writing it the result, and then plus 2k plus 1 times 2k plus 3. Now it is simply about making sure I do the right algebraic simplification. I have an LCM, 2k plus 1 times 2k plus 3. So my numerator is k times 2k plus 3 plus 1, and 2k square plus 3k plus 1 upon 2k plus 1 times 2k plus 3. Okay, this is what I got after I simplified my expression, and n upon, right, so I did it right till here. And now I want to make sure that how should it look like. This should really look like my RHS should have been k plus 1 upon 2 times k plus 1 plus 1. So it should have been k plus 1 upon 2k plus 3. So but my numerator looks very different from what it should have been. Correct? It is not really k plus 1 upon 2k plus 3. So the numerator doesn't have a 2k plus 1 factor common, or does it have? So let me find out if I can divide this numerator by 2k plus 1. So 2k square plus 3k plus 1, I'm going to divide it by 2k plus 1 to see if I really get that numerator. So k times 2k square plus 2k plus 1, sorry, plus 1 time, I'm sorry, here I multiplied it wrong, it was k. So 1 time, yes indeed. So the numerator is factorable, and I can factor it as 2k plus 1 times k plus 1. How did I get the idea? Obviously there is nothing else that should have been possible. If the numerator needs to have k plus 1 and 2k plus 1 need not be in the denominator, then there must be a common factor. So I could get it in this format that is required. So it is true for k plus 1 also, and therefore I have been able to prove that assuming n is true for n equal to k, k plus 1 also became true. So for each mathematical induction question, the main challenge is how do you make the right kind of simplifications when it is the k plus 1th term. Once you do it, the format remains the same. You start with one specific case for n equal to 1 or 2 or whichever number you want to say. You assume n equal to k is true, and then you prove for n equal to k plus 1.